Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future. We are almost done with this part on database design theory. We just have a few more slides to go, and then this is it. Then we'll move on to the next part. But before we start, I have, I think, two questions for you. So this is the first question. Which of the following are not unique? Some of these are unique, some of these are not unique. The closure of an attribute with respect to a set of functional dependencies. Is it unique? Is it not unique? The closure of a set of functional dependencies. Is it unique? Not unique? The minimal basis of a set of functional dependencies. Is it unique? Not unique? The superkey of a relation given a set of functional dependencies. Unique? Not unique? First, we do have two majority answers. And these two are not unique. The closure of an attribute with respect to a set of functional dependencies, and also the closure of a set of functional dependencies. Mathematically, what it means to be a closure is that you try to fill and fill and fill and fill, traversing some graphs. So transitive closure is another name for that. And so you keep adding things. These have the tendency to be unique, right? You just put everything you can put in there, and then you have the closure. So the closure of an attribute is basically everything you know, right? If I give you a few attributes and we play this game, then you have to throw into the bag everything you know. And everything you know is unique, right? That's the intuition behind that. So the closure of an attribute is unique, or even of a set of attributes. The closure of a set of functional dependencies, what we mean here is that if I give you a set of functional dependencies, you can apply the actions and the rules that I have given to you, and you can create many, many, many other functional dependencies that also apply. In practice, it's a very large set, right? When you try to put all the functional dependencies in there. And this one is unique, right? These are absolutely all the functional dependencies you can think of. This is a unique set. Now, the minimal basis of a set of functional dependencies, that's basically the kind of the opposite of the closure, right? So the closure is all of them. The minimal basis is as tidy and small as possible, but in an equivalent way. Now, there are more than one ways to clean up. And so the minimal basis is not unique. Depending in the order in which you eliminate things, you might not get to the same results. There is actually a very simple counterexample if you want to have one in mind. Imagine that you have A determines B, and then you have B determines C, and then you have C determines A. You basically have a cycle. Then you can revert the cycle. You have an equivalent set that would be A determines C, C determines B, and B determines A. They're equivalent. You just invert the direction. But they're not the same, and these are two minimal bases. So this is a simple counterexample that shows that they are not unique. And then the super key, you also know that there can be plenty of super keys, right? You can have a lot of super keys. Some of them are minimal. What do you call a minimal super key? A candidate key, and there can also be multiple candidate keys, right? That has to do with the fact that when we say minimal super key, it's not minimal in the sense of numbers. It's minimal in the sense of subsets, right? And so there's also multiple ways that you can find some minimal super key. So the last two are generally not unique. Who is with me? All right, then I have the next question to check that you are with me. So here's another one. I'm not testing your knowledge, but the knowledge of your knowledge. This is getting into game theory, like common knowledge kind of thing. So I just want to know what you can do and cannot do. So just answer honestly based on what you feel you're capable of doing. These are basically classical tasks or exercises that can be typically asked in database lectures, right? So for example, if I give you a table, can you tell whether or not a functional dependency applies to it? If somebody gives you a list of functional dependencies, can you tell whether or not a given set of attributes is a super key? If I give you a list of functional dependencies, can you tell whether or not a set of attributes is a candidate key by trying to remove attributes from it? Can you tell whether or not a table is in the first normal form? Can you tell whether or not a table is in the Boyce code normal form if somebody gives you a list of the applicable functional dependencies, looking at the left-hand side? If somebody gives you a set of functional dependencies, can you compute the closure of any set of attributes? That's the one where 100% got it right, remember? And if somebody gives you a set of functional dependencies, can you tidy it up, compute a minimal basis, not unique? So I just want to have kind of an overview of what is easy for you, what you really know how to do, what you still need to practice. So I get a lot of votes for many of them. This is very good, very, very good. Very good. Okay. So let me just quickly talk about the two that have less votes. To refresh, what is the first normal form? Can anybody remind me of that? How do you spot the first normal form? Yes? Exactly. All values are atomic. It means you can have strings, you can have dates, you can have numbers. What you cannot have is tables inside tables or objects inside tables or arrays inside tables, like anything structured you cannot have. So this is very visual. I give you a table, you should instantly see if it's in the first normal form or not, right? You just cannot have any nested structures. Can anybody remind me, because all of you said you can spot the super keys, right? So can anybody tell me for the Boyce normal form, how can you spot if a table is in the Boyce code normal form or not? Anybody remembers the definition? It's a very simple definition. You look at the non-trivial dependencies, and what should be on the left? What should you have on the left? Yes? Exactly. If you find anything that's not a super key on the left of any dependency, then it's not in the Boyce code normal form. If you want to be in the Boyce code normal form, everything that you find on the left of a non-trivial functional dependency should be a super key. So basically, since everybody tells me you can spot the super keys, then normally you should also spot the Boyce code normal forms, because all you need to do is use the super keys you found with the second answer, and you just need to check whether or not everything on the left is a Boyce code normal form, is a super key. For whom is that clear? All right. And really, remember, you should ignore the trivial dependencies. Whenever you have A determines A, that's a trivial dependency, right? So this one doesn't matter for the Boyce normal form. You need to look at the non-trivial ones, the ones that are actually informative. Okay? These are the two. So then a majority gave me, so the candidate keys, you basically take a super key and try to remove as many attributes as you can, but keeping it a super key, right? As soon as it's no longer a super key, then you cannot remove, right? So that's basically what a candidate key is. It's also not unique, right? But that's basically how it works. And the other one where there's not 10, the closure of a set of attributes. Here I'm surprised because when we actually did it, 100% of you found the answer, right? It's like the game. You just throw in the bag everything you can. You basically, I give you a set of attributes and a set of functional dependencies, and you basically look for the functional dependencies where everything on the left is already in the bag, and then you put in the bag what's on the right as well, right? And you keep adding and adding and adding until you can no longer add anything anymore, right? So that I know 100% of you can actually do it because you solve it correctly. And the minimal basis, this one is actually trickier, but it's kind of intuitive. And so we did it together a few times. So yes, I'm glad that most of you can do it. All right, so that should give you a good checklist. So if you don't feel confident in any of these, then just solve exercises, either from the exercise sheets that the TA teams gives to you or from the book. Okay, it's really just a matter of doing it. And once you've done it often enough, then you will see that it's, yeah. Oh, was there one below? Ah, yes. Oh, yeah, there's two. There is two below. Okay. So if you give me a table in a functional dependency whose left-hand side is not a super key, then I am able to decompose it. Who remembers how we do that? If a table is not in the Boyce code normal form, how do you decompose it? Do you want to answer? Mm-hmm. Yeah. Yeah. Exactly. Yeah, that's how it works. So I'm repeating for the people on Zoom, but you're absolutely correct. If it's not in the Boyce code normal form, then it means there is a functional dependency that is guilty of not having a super key on the left, right? So you take that functional dependency, could be also not unique, right? But you take one of these functional dependencies, and what is on the left is not a super key. Then what you do is the first table of your decomposition is you take the everything that was in that guilty functional dependencies, right, from the left and on the right. Do not forget to compute the complete closure of what's on the left. You really need to compute the closure of the set of attributes. And because it's not a super key, that will not be the whole table. You will still have missing columns. So the first table is the transitive closure of the left-hand side of the guilty functional dependency. And the second table is made of the left-hand side as well, plus all the missing attributes, the ones that were not in the transitive closure. For whom does that make sense? Right? And then you iterate and iterate and iterate until everything is in the Boyce code normal form. This is also not unique. Right? If different people do it, you might arrive to different decompositions. So this is fine. Okay. And the chase algorithm, you don't like the chase algorithm? So it's a little bit of a bingo game. Who played bingo already? Right, you know the bingo. So this is really a bingo game. You basically start by setting up a table where you put the ABC that correspond to one side and let's say CDE that corresponds to the other side. And then you use the functional dependencies in order to use that you have A and A1, you know they're the same, so you replace A1 with A, right? And as soon as you have a bingo with A, B, C, D, E, F, like the full row, then that's it. You're done and you've proven that the decomposition is lossless, meaning that what was in the join was also in the original table. For whom is that clear? All right. So the best advice that I can give you is do it. Do it. The past exams are full of opportunities to try to use the chase algorithm. And also in the exercise class, you will have some examples of it, right? What I can tell you, just to be sure that it's clear in your minds, if you use the decomposition that I told you about, using guilty functional dependency that doesn't have a super key on the left. If you use that one, it will be lossless. So I just gave you a way to win at the bingo every time, right? You're guaranteed to be able to have the bingo when you actually use this algorithm. But you might have other decompositions that did not follow these rules, and then you might not win at the bingo. Then the chase algorithm actually doesn't succeed, and you can prove that then the decomposition is bad. It's not lossless, so that's not a good decomposition. Okay, and now I think we are done. There's nothing left below that, right? So that's a lot of things to practice, but again, the nice side is that it's just a matter of repeating, reading it all over again. Okay. So now I am going to go back to the very few slides that still remain. Don't have to be scared. I have almost nothing left to throw at you from database design theory. So I was just talking about that actually. So that's a good transition. So now I told you how you can decompose a relational table. If it's not in BCNF, Boyce Code normal form, you can turn it into several relational tables that are each in BCNF, and such that it is lossless. Lossless means the bingo wins, right? It means that when you join back the tables in the decomposition, you get exactly the original table. This is what we call lossless. The information before and after the decomposition is exactly the same. Okay, for whom is that clear? Very good. Now, we still have a problem, and we kind of have to live with that, is that it might be that when we look at the functional dependencies of the decomposition, not all of the dependencies of the original table might survive. So it happens that you lose some of them. So I think in particular, when you have functional dependencies that involve columns of several tables in the decomposition, then some of them will not survive because in the decomposition, you can only have functional dependencies within the same table, right? So we just have to live with that. That's how it is, right? So it's lossless, it's in BCNF, but some of the functional dependencies might get lost. And that actually gives us a beautiful, is the clicker on strike today? Yeah. So this is an impossibility triangle, right? So they're everywhere, the impossibility triangles in life, right? So for example, in that case, you cannot have at the same time generally an algorithm that always gives you tables in Boyce Code normal forms and that is lossless and that preserves all the dependencies. That doesn't exist, right? So what I showed you is BCNF and lossless, that you give up some dependencies. Of course, you can try to tweak the triangle somewhere else, right? You can have BCNF and you preserve the dependencies, but the problem is that you're losing information. That is absolutely not recommended to do that in real life. And you can also just drop the Boyce Code normal form, but it's lossless and dependency preserving, right? That actually works. What do I mean with abandoning the Boyce Code normal form where you basically target lower normal forms? Do you remember what number the Boyce Code normal form has? 3.5, right? So 3.5, and so it means that we have the third, we have the second, right? So we can go down. Speaking of which, I think this is the next slide that is coming. Yes. Normally in the bachelor's level of computer science, what we do is that we spend actually a lot of time on the normal forms, much more than we did in this course. In fact, we don't directly teach the Boyce Code normal form. What we do is we teach, so the first one is easy that I showed you. Then we look at the second one, then we look at the third one, then we look at Boyce Code, and there's even a fourth and a fifth and a sixth normal form. But in this course, I didn't spend too much time on the second and third normal form. I directly gave you the Boyce Code normal form because this one is very easy to spot, right? Just look for everything is a super key on the left-hand side. However, what I can do is just on one slide, give you a very high-level characterization of the second and third normal form to make it obvious that everyone is stricter than the previous one, right? The higher up the number, the stricter it gets. Now, if you look at the actual definitions, they're super complicated. Even I have really headaches when I look at these definitions, which is very surprising because, in fact, you can also explain it like this in plain English, and this is actually rigorous to explain it in this way. So this is how I remember how the normal forms actually work. So this is the Boyce code normal form, right? And I told you that an attribute cannot depend on anything that's not a super key, right? That's what we've rehearsed just now, right? Any attributes, we don't care if it's prime or not. You remember the prime attributes, non-prime prime attributes? What is that? What was the prime attribute? Anybody on Zoom remembers what a prime attribute is? Nobody? Well, let me tell you what a prime attribute is. When you look at all the candidate keys, you know, you can have several candidate keys, the minimal super keys. Well, it's easy. Every attribute that is in at least one candidate key is called a prime attribute. That's what it means, right? So it's a prime attribute. Anything that is in any candidate key is a prime attribute. A non-prime attribute is an attribute that is never, ever in any candidate key. And here you can think as the examples, quantities in inventories or prices, like this kind of attributes, because a price doesn't determine something, a quantity doesn't determine something, right? So these are the typical non-prime attributes, like price or quantity. But in the Boyce code normal form, we don't care, right? We just do not want something that's not a super key on the left, and it doesn't matter what we have on the right. We don't care, right? So prime or not, we don't care. So one way to weaken the Boyce code normal form and be slightly less demanding is that we forbid non-prime attributes, so price, quantity, that sort of things, to depend on something that's not a super key. But if we have something that's not a super key and that determines something that is prime, then we are kind of okay with it in the third normal form, right? We say, okay, that's fine. It's not a price or quantity, it's a prime attribute, right? So the idea is you have something that's not a super key that points to attributes that are in some candidate keys. And here we close our eyes, we condone it, we say, okay, that's fine. That's in the normal form, the third normal form. Who sees that this is less strict, right? Because now we close our eyes if the attributes on the right are basically prime. So this is the third normal form. Then the second normal form is even less strict. In the second normal form, what we don't want is something on the left that is a strict subset of a candidate key, right? That leads to a non-prime attribute. So what we change now in terms of what we demand is what we have on the left, right? So you agree that something that is a strict subset of a candidate key cannot be a super key, right? That's the definition of candidate key. If you remove anything in the candidate key, that's no longer a super key, right? So a strict subset is a candidate key, that's a particular way of not being a super key, right? It's just more restrictive. So basically, in the second normal form, what we forbid is something on the left that would be a subset of a candidate key, a strict subset, and that has on the right a non-prime attributes, right? But now, what we do in the second normal form is that we close our eyes. If we have something on the left that's not a super key, we close our eyes if it's also not a subset of a candidate key, right? If it's not a super key, but in another way than being a subset of a candidate key. Then we say, okay, that's fine, that's the second normal form. So you really see that it's just a cascade of demanding more and more demanding, right? Non-prime attribute cannot depend on a strict subset of a candidate key. Third normal form, we are stricter. Anything that's not a super key, whether a strict subset of a candidate key or in another way, anything that's not a super key. Then we go from the third normal form to 3.5, so Boyce code, by requiring that not just the non-prime attributes, but any attributes cannot depend on anything. Okay, so this is the idea. We won't really practice the second and third normal form. The one thing I want you to remember is just that every higher normal form is stricter than the previous one. So you really have the first one, then the second one, then the third one, then the 3.5 one. For whom is that clear? right? So I just wanted to give you an intuition. And I didn't put any mathematical formula. If you want to see the mathematical formulas, they are in the book and they are even on Wikipedia, probably. So, yeah. Okay. I think this is the last slide of the database design theory. And I didn't bother you with the fourth and fifth and sixth, so we can actually go even with even more demanding hypothesis. Okay. In practice, so Boyce code is easy to spot. A lot of people actually are quite happy with the third normal form, right? So if you have a web shop and you're in the third normal form, then that's kind of nice, right? It's sufficient. And why did I mention that? Because if I correctly remember, if you only demands the third normal form and not Boyce code, then you get the whole triangle, right? You can be in the third normal form, lossless, and dependency preserving, right? So that's one of the benefits of being less demanding, is that then you get all three conditions, right? Third normal form, lossless, dependency preserving. Okay, so here I stop with database design theory. Are there any questions? Anybody? Anything you want to know on Zoom? Okay, so you can still ask questions on the forums to the TA team. You know, we're always here to help. And again, I cannot repeat enough. Do the exercises. Practice, 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 practice. This is really the way of making yourself familiar with these things. Okay, we will release, if we haven't already done so, we will release all the past exams on the Moodle at some point, and then you can look at what there was before. There's a lot of such exercises. Let me stop the recording here.